I am AI. Accelerating your discoveries to solve the great challenges of our time. I am a visionary, bringing characters to life with more natural movement, generating brilliant new worlds for them to explore, and inventing new ways to bring out the creative genius in us all. I am a protector, leading the way into the most dangerous environments and searching for signs of life. I am a guardian, listening for the sounds of destruction to save our forests, and using satellites to bring freedom to those who are enslaved. I am a navigator, finding safer paths for cross-country deliveries and taking personal travel to new heights. I am a scientist, exploring oceans of data to understand extreme weather patterns and studying the building blocks of life to save a community from hunger. I am a healer, giving hope to those who suffer from the most challenging diseases. And tapping into the brain to rejuvenate paralyzed limbs. I am even the composer of the music you're hearing. I am AI, brought to life by NVIDIA, deep learning, and brilliant minds everywhere. Ladies and gentlemen, please welcome NVIDIA founder and CEO, Jensen Huang.
So this is what it's like to be Kobe playing in the great stadium. Hey guys, thanks for coming out this way. You know, we got so packed in the old stadium that we had to get you guys out here, so I really appreciate you making the trip. I have so much to tell you guys today, so many fun things to tell you. I'm going to get going right away. The accelerated computing approach that we pioneered is really taken off. If you take a look at what we've achieved last year, the momentum is absolutely clear. 50% more developers on NVIDIA GPUs, 50% more CUDA downloads than a year ago. We now have 140 supercomputers powered by NVIDIA, a 50% growth, the #1 fastest supercomputer in the world, the Summit, the #1 fastest supercomputer in Europe, the Swiss Supercomputing Center, does paint, and the #1 fastest in Japan. 22 of the most energy-efficient supercomputers are powered by NVIDIA. We now have 600 applications that are powered by CUDA in high-performance computing. 15 of the top 15 applications most popularly used are now powered by CUDA. And this year, we saw some really important new applications. CryoSpark, the reconstruction of particles from cryo-electron beam microscopy. Fun3D, a CFD simulation. GROMACS, molecular dynamics. Microvolution, a inverse convolution method to enhance imagery, parabricks, genomics analysis, and WRF, the world's most popular, most frequently used weather simulator. The thing that's really great about a software-defined method and an accelerated computing approach like ours is that we never give up on the applications, and together with the developers, we continue to advance it. Using exactly the same GPU, exactly the same infrastructure, applications continue to improve in performance. If you take a look at some of the most popular applications from a year ago, this year over year, we improved the performance from 25x to almost 40x. We continue to enhance those applications, continue to refine them, continue to squeeze more performance out of them so that you can continue to be more and more productive or simulate larger and larger simulations. Accelerated computing is not just about the chips. The chips is really important. There's no question about that, and we certainly build the world's largest chips. But accelerated computing is a collaboration, it's a co-design, it's a continuous optimization between the architecture, the chips, the systems, the algorithms, and the applications. The NVIDIA stack looks basically like this. And today I'm going to refer back to this repeatedly. Starting from now, we're going to take all of our libraries and we're going to put them together into one body of work, one suite, if you will, one umbrella name called CUDA-X. CUDA Acceleration Libraries. It's built on top of the architecture that all of you know very well, and for many of you, the reason why you're here, called CUDA. CUDA runs on top of all of our GPUs. It runs on top of our graphics GPU called RTX, our deep learning systems called DGX, our hyperscale systems called HGX, and even our autonomous machine systems, our little embedded systems called AGX. It's architecturally compatible with all of them. On top of it, we build domain-specific acceleration libraries. Domain-specific acceleration libraries. One domain after another, whether it's in computer graphics or high-performance computing, artificial intelligence, autonomous driving, DR for drive, IS for Isaac, robotics, CL for Clara, healthcare, medical imaging, and the last one is what? Metropolis. Metropolis for smart cities. All of these domain-specific applications and acceleration libraries are now contained as part of what we call CUDA-X. And on top of it is NGC, the NVIDIA GPU Cloud. Whenever it's possible for us to containerize those libraries, we do so. And we put it into the NVIDIA GPU Cloud. You could download it into any cloud, any data center, any computer that has been certified, and it will just run. The entire acceleration stack, fully integrated, fully optimized, and enhanced all the time. Now, the reason that we do this is for several characteristics that we really love about accelerated computing. And remember, it's not just about the chip. It's about the entire stack. And so one way to think about that is this. The first thing you want to do for accelerated computing is you want to make it programmable. I created a whole bunch of acronyms here just to simplify it for you. And more importantly, that's right, I made it simple for you. More importantly, there's going to be a pop quiz at the end. Okay? There's going to be a pop quiz at the end. It's programmable. Well, the reason for that is because most algorithms today want to be software-defined. You want your computers to be software-defined because so much innovation is going into computer algorithms today. And we want to put the architecture, put the computer, put the capabilities of that machine in the hands of the software developers. Making it software-defined makes that computer forever more powerful, improving all the time. If it's software-defined, if it's programmable and has great tools, then the time to solution, time to finding that algorithm will be shortened. And of course, you will see growth in the number of domains, growth in domains. If it's programmable, you could use it for more and more things. The number of algorithms, of course, are diverse and endless. But the fundamental computational methods tend to be very similar. And so by using a software-defined acceleration approach, we could expand the number of domains that the computers could be used for. Acceleration gives you time to answers. Time to answers or size of problems. You can increase the size of the problem. Whether you want to take a very large problem, do it as fast as you can, or you have a certain amount of time, you want to increase the size of the problem you can solve. It also gives you the lowest cost of infrastructure. If you solve a problem quickly, if you have a computer that can achieve the necessary solution as quickly as possible, of course you could buy fewer computers. You've heard me say, the more you buy, the more you save. The reason for that is this: doing things efficiently and doing things quickly is the most cost-effective way of doing something. The number of domains. It turns out a computer is only successful if there's a whole ecosystem around it, and the number of partners that you have that take it to the marketplace is large, because the world that uses computers is huge. Almost every field of science, every industry, every company in the world uses computing of some kind. And we believe that in the future, they will all be high-performance computing customers. They will rely on high-performance computing to achieve their mission. The cost of deployment is lowest when it has multiple domains. And the reason is very, very simple. A computer maker would be more enthusiastic to take computers out to the world if it can serve finance and healthcare and manufacturing and transportation and retail and insurance. The larger the number of domains that a computer serves, the lower the cost of deployment it is. It is the reason why today the x86 is the world's most affordable and the most popular computer, because it has so much use. The space of applicability is gigantic. Its domain of use is large. Programmability gives us the largest possible domain. It also, as a result, reduces the cost of infrastructure again. Architecture. Architecture is a funny word. In our company, architecture means this: an application that was written yesterday has to run on a computer tomorrow. And an application that we enhance today will run on computers everywhere that has CUDA in it. Architectural compatibility has such enormous and powerful implications. It is the reason why architectures either succeed or don't succeed. Backwards compatibility, large installed base, all makes it available to drive the cost of the infrastructure down. So the architecture gives us continuous improvement in performance. It expands the domains and drives the cost of infrastructure down. All of these things create a positive feedback system, and that's what we're experiencing today. The reason why an architecture grows faster and faster and adoption grows faster and faster over time is because of these characteristics. Well, these characteristics, as it turns out, is incredibly hard to remember. And so, as in every keynote, I try to introduce you to a new word. Today's word is, that's right. And I come up with it at the very beginning of every keynote, just in time. And so this is the word of the day, Prada. At the end of our keynote, I will ask you this word again. Prada stands for Programmable Acceleration of Multiple Domains with One Architecture. Does that make sense? Prada. Can you remember this? Okay, say it out loud. One, Prada. Okay, thank you very much. My job is done. Have a nice day. Okay, Prada. Accelerated computing, the approach that we pioneered a dozen years ago, is really taken off. And it's taken off because we're seeing that CPUs are not scaling as fast as they used to, and because the number of workloads that are really, really important to the future of computing and future of society has just gone berserk. The amount of computation that is necessary for the future is incredible, and I want to talk about some of those today. But first, my talk is in 3 chapters, 3 fun-filled chapters. The first chapter is computer graphics. Computer graphics, the driving force of our company. It is the simulation of virtual reality, one of the most challenging computation problems in all of the industry. After 25 years of pursuing real-time virtual reality, we have not achieved it, not even close. But we're getting closer and closer every single day. Today, I want to show you something that's really great. This is by one of our partners, and I'll come back and I'll tell you about it in just a second. Run it, guys.
Invent yourself, and then reinvent yourself. Don't swim in the same slough. Invent yourself, and then reinvent yourself. And stay out of the clutches of mediocrity. Invent yourself, and then reinvent yourself. Change your tone and shape so often that they can never categorize you. Reinvigorate yourself and accept what is, but only on the terms that you have invented. Be self-taught and reinvent your life because you must. It is your life, and its history and the present belong only to you.
Okay, was that real or virtual reality? Let's take a look. All right, audience participation, okay? Left is real or right is real? How many people say right? This is not real. So how many people thinks this is real? It's got to be the rest. Come on. Okay, so everybody thinks this one's real. All right. Next one. How many people thinks this one's real? Getting a little confused. How many people thinks this one's real? Okay, so this one's real. All right, this is one of those rock, paper, scissors things. All right. How many people thinks this one's real? Okay. Well, it turns out they were all on the same side. This one's not real. This one is RTX. That one is real. Isn't that amazing? By mimicking the physical properties of light, RTX has made it possible for us to perform real-time ray tracing for the very first time. It turns out ray tracing can be done in software. It is true. And the reason for that is because the first implementation of ray tracing was done in software by one of our researchers a long time ago. And in fact, most films are software ray traced today. They're run on a bunch of CPUs. They call them render farms. There's about 1.5 million of those render servers running around the world, making movies all around the world. And so it stands to reason that ray tracing could be done in software. But as in everything else, our goal is to accelerate this particular domain of application. What we want to do is find a way to accelerate enough of it as quickly as we can so that it can be done in real time. Chad is going to show you a couple of these things. Chad?
Yep.
What are you going to show us here?
So the one thing I'm going to show you, which is is the new thing, is what is not very common in that video you saw, is all those rendered image you would see would have been done offline over a few minutes, a few hours, even days. That video you saw at the beginning that we did with Unity, all the rendered images were done in real time on a RTX hardware. And so some of those images a lot of those scenes were rendered about 30 FPS, and what we're showing you right here now is not a cut from the commercial we kind of put together. It's actually Unity running real time.
Wow.
And so
that's amazing.
Yeah. So this would be really useful for like a designer, a professional designer who's like, I want to see what my materials look like simulated for real using ray tracing. So they could swap materials. They can play with the compartments, open them up, see how the lighting works.
Guys, this is all done in real time.
Yep. We can even go to the exterior. You'll see some of these shots where we're familiar. Again, you can change the materials. Make sure you didn't create any distracted reflections for other drivers or anything like that. And kind of play around, and we can turn some of the RT effects on and off to show you what's really going on. So ray tracing gives you like a real shadow. And then you turn it back on, and there you go.
That's beautiful. Chad, thank you very much.
A quick thing, real exciting about it is we're showing this in Unity. It looks awesome. It's actually going to be available in an experimental package April 4th. So it's coming soon for everyone here to play with.
April 4th. All right, guys, Unity, great work. Thanks a lot. Dan Vivley, you're in the audience. You must be very proud of Chad. Chad Vivley. All right, we practically raised him. Okay, so this is the NVIDIA Turing RTX architecture. It is the greatest leap in computer graphics in 15 years since we started the programmable shader revolution. If you take a look at the imageries today, it's really at the limits of what you could do with programmable shading, and we need to kick it up a notch, take it to the next level of realism. What you saw was a 2080 Ti, the highest end of the Turing architecture, 18 billion transistors, 32 trillion operations per second. 16 trillion of it floating point, 16 trillion of it in integer. The reason for that is for the first time Turing's architecture split the integer and floating point execution so we can do them concurrently. The reason for that is this. Back in the good old days, we would largely use our GPUs for shading. But in the future, if we want to use it for ray tracing, the programs are really complicated. And when you do a lot of complicated program execution, the integer or the address calculation of the program becomes to dominate. And so by making it concurrent, we could overlap the shading operations as well as the ray tracing operations with concurrent float and integer operation. We also have the new technology called variable rate shading. Depending on what part of the screen it is, maybe the amount of shading doesn't have to be nearly as precise. Maybe the texture is relatively coarse. Maybe it's moving relatively fast, so you wouldn't notice it anyways. Using variable rate shading, we could reduce the amount of shading necessary. We have this new technology called mesh shaders. Allows us to render really, really complicated scenes like rocks and geometries of mountains and enormous forests of grass and rocks and just, stuff in the world. Stuff in the world to make it more interesting. Render stuff. It's called the incredibly fast stuff rendering system, otherwise known as mesh shaders, and it allows us to do things like level of detail adjustments. And of course, the big ticket item is ray tracing, our first GPU to be able to do ray tracing and intersection testing in real time. And then lastly, one of the most important features of this GPU is a tensor core architecture. It allows us to do artificial intelligence for generating images, creating pixels that otherwise would have had to been rendered or fully calculated. And so notice the number of things that you can now do with artificial intelligence with super resolution. If we could find a way to create algorithms and neural network models that can process it so fast, we could reduce the number of pixels we calculate, infer the rest of it, and as a result, achieve very high performance. We're working on this part. It's called DLSS. We're making progress all the time. I'm super excited about its future. There's no question in my mind this is going to be a huge success. We just have to continuously innovate and create these new models. Well, creating the GPU is the first step. Inventing the technology is the first step, but ultimately what's going to enhance its adoption is the entire ecosystem supporting it. And the ecosystem starts with the most pervasive computing platform for 3D in the world, Microsoft Windows. And Microsoft Windows DirectX with ray tracing called DXR is now available. But that's just the API. That's the lower level API. On top of it are the game engines. The two most important game engines in the world, Unreal and Unity represent 90% of the world's games. You just saw just now Unity with DXR and RTX acceleration, as Chad said, available April 4th for people to download and experiment with. We also mentioned before that Unreal is developing their version of game engine, as Unreal Engine 4.22, which will incorporate DXR. And then lastly, Vulkan RT. These represent basically the entire, vast majority of the entire computer graphics industry. And it is all coming together for a future of ray tracing. Then we have to create all the products. We now have Turing RTX graphics cards from top to bottom. From what you saw earlier, which is a 2080 Ti, we recently announced a Turing GPU for just over $200, $219. The lower-end GPUs have no RTX, just the Turing shading architecture. And then for the higher-end GPUs, starting with the 2060, whenever it says RTX, it has the ray tracing acceleration hardware. But the Turing architecture now spans from $219 all the way to the highest performance in the world. And this year, we have more notebooks than ever. The gaming notebook marketplace is growing super fast. It grew 50% just at NVIDIA last year, year over year, and we expect this year to be pretty great as well. 40 new laptops based on the Turing architecture has been announced. Let me show you a couple more demos. It is very clear that ray tracing is the next step in real-time computer graphics, and the next generation of video games has started. This next game I want to show you is from a developer called Nexon, and it's built on top of Unreal Engine 4.22. Really amazing. I think it doesn't matter how the technology works. Many of you in the audience understand how the technology works. It's really a marvel that we're seeing real-time ray tracing, but what really matters in the final analysis is that things just look so much more beautiful and alive. You know, everything is just alive somehow because the reflections work properly and the shadows work properly. It just looks much more realistic, much more alive, and as a result, developers can tell much better stories. It all started about 20 years ago. About 20 years ago, for the very first time, hardware 3D acceleration was possible because of a game named Quake. It uses OpenGL for the very first time. Frankly, Quake, if it wasn't because of Quake, NVIDIA wouldn't be here today. Every company needs a bit of a killer app. And in our case, it was the video game industry, and the one that really kicked it into high gear was Quake. And it was so hard to render Quake back then. It was just so hard to do it, and you needed an accelerator to do it. And for the very first time, we were able to do Quake in real time. Now, our engineers wanted to do something and make a contribution technologically to the community that has since worked on Quake. It turns out Quake has gone through several different iterations, and what we're going to show you is Quake 2. It's open sourced, and this is going to carry on some of the work that was done by Christoph Schied, one of the interns at NVIDIA, working at NVIDIA Research, and we took it all the way. And what we're going to show you here is an original game now done with state-of-the-art computer graphics. Manuel, let's show it to him.
All right, so what you're looking at over here is a resurrection of the original single-core, single-thread running on a CPU Quake 2 game engine. And this is one of the deathmatch maps. And at the time...
Our CPUs are so fast now compared to 20 years ago, you could just render it in software using a CPU. Go ahead, Manuel.
Of course, at the time on a single CPU, you just really do not have compute power to do global illumination. And instead, they used light maps. So all the lighting is baked and static, and this is what you get. Now, what we added on top is RTX so that we can do this.
No. Ladies and gentlemen, wait for it. This is not the end. This is the beginning. Wait for it. All right, Mel, go.
Everything is dynamic. We can change time of day. We can move around, all the reflections.
The materials are physically based. Go ahead, keep going. We'll just keep going. Go. Manuel.
Yeah, at this point, I'm just letting them run because it's just so beautiful. So Alexi over here, who's the lead programmer, has added a lot of features. So the first thing we did was adding high dynamic range, because without physical units, nothing works, obviously.
The direct lighting, the indirect lighting, the reflections, the refractions, all based on ray tracing, all based on path tracing.
Once again, the CPU rasterizer over here with baked global illumination and RTX. All right, we're going to take you to one of the actual game levels for gameplay.
All right, so this is before?
This is before. This is after. As you can see, we now have physically based material. We can get glass, which reflects everything around it. We also added little fun things like volumetric lighting that you can see here with beautiful light shafts. And we have more interesting materials coming up, like metal grades over here, which start reflecting all the environment around them. No tricks. This is actually real. We're not faking it. And here's another little Kodak moment. There we go. With beautiful volumetric lighting, very moody. Again, before and after.
Ladies and gentlemen, this is a definition of beauty for a computer scientist.
And we have one more little surprise for you. Something else that we've added at the last minute. We weren't sure if it was going to work today. So I'm going to let them show it. And of course, this is not Quake without a BFG.
Okay. All right. Okay.
Thank you.
Alexi, good job. Manuel, good job.
Thank you.
This really incredible work. And obviously this is a work of love. We're going to contribute this back to open source, and the engineers are going to finish it off over the next month. And stay tuned, and we'll post it as soon as we can. But this is genuinely state-of-the-art computer science and computer graphics coming together, and we're doing it in real time. And when we put it out in open source, it's going to be a topic of great research and great discussion to advance the future of computer graphics. So that's real-time computer graphics. offline computer graphics, or rendered using render farm computer graphics so that we could generate photorealistic images is used in every single industry today. Whether it's in architecture or product design, there's a whole community of 3D artists who use 3D graphics and rendering software to create amazing imageries. This is created by somebody. It's a fan out there who just loves to create art with this medium, arduously, meticulously turns their imagination into something that comes alive. And of course, media and entertainment, using it for making movies. A modern movie might have something along the lines of 2,500, 3,000 shots, and each one of those shots are a few seconds long, just a few seconds long. And those few seconds would take a team of tens and tens of artists and designers, and it would take them literally the time of the film-making production budget time to create those few shots. Whole bunch of studios were coming together and stitch all of their shots together and creates what you guys know, what we all know as a wonderful movie. Well, this process is incredibly arduous, and we wanted to bring accelerated computing to the rendering process for the very first time. This has been largely the effort of CPUs because the algorithms are so complicated. The data size is so large. It has taken us literally 25 years to do this. And so finally this year we announced RTX, and we started working with all of the leading film quality design tool companies and firms to accelerate their tools and rendering systems. And I'm happy to announce that as of now, over 80% of the world's leading tools makers and film studios have adopted RTX, and by the end of this year, we should have all of them in production. We have some of it in production now. Arnold is ready, and we're going to show you some examples of some of the work. This is from a studio called Image Engine, and this is work that they did for Lost in Space. I can't wait for the second episode, second season. Let's take a look at it. Image Engine, Lost in Space. And you could see the work is arduous, it's meticulous. It takes so many people working together to create that one shot. It's layered by layered by layered, a meticulous process, what we ultimately see as the final film. What you saw there was really quite amazing. So in just a few seconds, it represents a shot. Our early adopters, our early developers, have now benchmarked it for us. This is, take a look up here. This is the CPU with the Dual Lake server, okay, Dual Skylake server, 25 nodes, takes 38 hours to render a shot of a few seconds. A shot, of course, of a few seconds is 30 frames per second, and each one of those frames are meticulously rendered. 25 nodes takes 38 hours. The power bill is about $70,000 over the course of 5 years, and the total cost of that data center, or excuse me, those 25 nodes, is about $250,000. We've now done the same work, that one shot, with one node of what we call an RTX server, with 4 RTX 8000s. It took 6 hours instead of 38 hours. The cost of the server is $30,000, not $250,000. And the amazing thing is this. In the power bill that you would save, you could buy a server. Just with the power bill that you save. I used to say the more you buy, the more you save. I think I was wrong. RTX servers are free. And you get another $30,000 to spare at the end of 5 years. So it's completely free. Okay? And so I said earlier that doing work efficiently is the most cost-effective way of doing anything. And of course, energy efficiency and getting things done quicker is really a great savings. If you take a look at a major film, and it costs something like $350 million or $300 million to produce that film, and the vast majority of it is post-production, which is otherwise known as rendering, and it might take something along the lines of a year to a year and a half. If you could even save 1 month on what is otherwise a 1 year-long project, the amount of money you could possibly save is in the millions. And so this is one of the reasons why this industry is such in a hurry to find ways to accelerate the rendering process and to accelerate the production process. We're working closely with Pixar, and they've been so excited about the technology. I can't wait to see the first major motion movie made by Pixar rendered completely on RTX. The process of creating these movies are hard. It starts with modeling, and of course, you've got concept, you've got modeling, you've got texturing, you've got rigging, which is basically putting the bones into the characters. And once you put the bones into the characters, that character essentially becomes a robot. You can animate that character. You could deform it. You could change the shape of the skin. You, of course, do forward kinematics. You could do inverse kinematics. And so as a result, you can animate these characters. You have to light it, and then, of course, you have to render it. Make it look totally perfect. And then once you create the character, you have to composite it with a whole bunch of other characters and the scene and all the environments and all the special effects. All the special effects are done in physics simulation. It is so complicated. And I just told you that a shot may be assigned to, a few shots may be assigned to a studio. A few shots could be assigned to another studio. As a result, multiple studios and multiple sites are all working on a movie at the same time. There are over 200 animation studios in the world today. Because of the nature of how we enjoy entertainment, because so many cultures are now starting to adopt this form of this media and this form of entertainment, and because there's just so many different ways to enjoy content today, the number of studios have gone up significantly. And the amount of pressure that is put on the studios is increasing as well. They would like to drive their costs down. They would like to increase their productivity. But one of the greatest things that they want to do is find a way to work together. If you take a look at this map, this just represents a few of them. There's over 200 of them. And there are sites all over the world. And yet, some of the sites are working on modeling. Maybe another site is working on the simulations. Maybe another one's working on animation. They're all using different tools. Some of it is internal. Some of it is third party. And it's got to come together in some kind of a holistic way. Could you imagine a world where there was no way to share documents because the content is too big, because the workflows are too complicated, and yet each document requires hundreds and hundreds of human hours to do? Well, for Word documents, we have Google Docs. Well, for 3D content creation, we have nothing. We have nothing. And so we wanted to create a tool that made it possible for studios around the world to collaborate. For the workflow, the designers of a single workflow, which has all these different tools and all these different steps, to be able to collaborate. We've been working on this for some time, and I want to show you this great new technology from our company. It's called the Omniverse. The Omniverse basically connects up all of the designers and studios. It works with every tool. We communicate with all the tools through their plugins using USD and using MDL. And we only exchange all the things that are dynamic, and we put it into this world, this portal that everybody can see from. And so as a result, irrespective of what tool or what part of the workflow you're working on, you will see one version of the final content that you're creating in its highest possible fidelity. You could be on a laptop. Maybe your computer doesn't have ray tracing. Maybe you're using a particular tool. Its render is not quite up to the point of being able to do ray tracing. But all of you are working together in one workflow, and everything looks beautiful. Everybody has one common understanding of what everybody is working on at that moment in time. It's an open collaboration tool. It works with all of the major 3D tools out in the world. We're getting great support. People are so excited about this. Let me now show it to you. Ladies and gentlemen, the NVIDIA Omniverse. Now, we're going to demonstrate this very quickly. This is our team back there. And let's pretend for a second that they're all working in a different place. It doesn't matter. They're here today, but it doesn't matter that they're in different places. The Substance Painter could be done in Montreal. The Unreal Engine could be done here in California, and the Autodesk Maya could be done somewhere in England. And all these tools, all these studios are global, as I mentioned, and they're working on different parts of the design. Now, notice, in the case of Maya, we're doing the design. In the case of Unreal, we're composing the environment. In the case of Substance, we're painting that airplane. And these three designers don't see what the other ones are doing. They can't see what the other ones are doing until Omniverse. These three tools are from three different developers and three different third-party vendors, but yet we're going to have them see each other on the same Omniverse world. Okay, so what you're looking at over there is Omniverse. Now check it out. While one designer is changing the geometry, while another one is changing the scene, while another one is painting, it all shows up in one world. Can you guys see that? It's all showing up in one world. The geometry is changing. We could change the paint. We could create a different environment. This is Omniverse. Those are all the independent designers working separately. This is rendered with ray tracing. It doesn't matter what they have. And as a result, we have this beautiful world. Now, Omniverse could run on your local workstation if it has an RTX in it. It could also run in a local workstation, and you could share it with other people. You could stream it to other people in your work group. You could also put it in a data center, or you could put it in a cloud, and we can render all of that and stream it to you. It doesn't matter how you would like to enjoy it. Omniverse is one shared world. What do you guys think? Okay, so we're working on this. Thank you guys. Let's come back to the slides. The studios we've talked to are so blown away by this. This is something they've been looking for a whole long time. And finally, we have essentially the Google Docs for 3D design, except it also works across all the heterogeneous tools. And all the data formats are different, but when they communicate with us and connect into the Omniverse, this is what you get to see. We have early access planning. And come to this website, come to the NVIDIA website for developers, and it's under NVIDIA Omniverse. And let us know if you would like to have early access to that. Rendering is data center graphics. Omniverse ultimately will be data center graphics. Another data center graphics is GeForce Now. We've been working on GeForce Now for a few years. In fact, we've been working on it for about 6 years. And the reason we've been working on it is because it turns out that the vast majority of the gamers in the world don't have access to a powerful graphics card. We have some 200 million GeForce gamers in the world, and they're growing. But yet, there's another billion PC gamers that don't have the necessary computer or don't have a GeForce card to be able to play the games at the level that they should. And so we decided several years ago that we would create a cloud gaming system not a service, not a store. It's not the Netflix of gaming. It's an open platform so that all the developers get to keep all their economics. All it is a PC in the cloud. Think of it as a GeForce PC in the cloud. So whatever a GeForce PC can do for games, this can do. It's an open platform. It should be able to run everything. If it runs on a GeForce PC, on your desk, on your laptop, it should be able to run it in the cloud. It is virtualized so that we could share it across a whole data center and to be as efficient as possible. But yet the entire stack has to be exactly the same as the stack that we have on PCs because we want the software to just run. No porting, no onboarding, it just works. And it would be streamed to PCs, the other billion PCs that we can't reach. And that's what GeForce Now is about. There are 500 plus games in there today. Basically the games you love and enjoy on PC. If it's on Steam or the Epic Store or Uplay, all these different game stores, if you've bought it, if you bought the game and you get on top of GeForce Now, you should be able to stream it to a Mac, a Chromebook, a low-end PC, a laptop, a leftover PC from years ago. You'll be able to stream, basically, very high-quality games to that. GeForce Now has over 500 games. We have 15 data centers. About 300,000 users, players, are using it all the time now. We've been in beta for some time, and there's 1 million gamers on the waiting list. 1 million gamers on the waiting list. And we're trying not to tell too many people about it because the waiting list is actually fairly large. And so we're sitting here trying to improve the quality of our service, improve its reliability. It's a very complicated problem. We want to make sure the latency is as short as possible, never any hitches. The sound quality is excellent. The interactivity with the mouse is great. And what we've discovered is this. You could build the world's largest data center, it won't make any difference. You've got to build a whole bunch of data centers all over the world. And it turns out that the number of gamers around the world is quite large. And they're spread out all over the world. And so what we need to do is we need to come up with a system that allows us to go well beyond these 15 data centers to support these 300,000 gamers, but to find a way to reach all of the edges of the world through partnerships. And so we created this idea called the GeForce Now Alliance. The GeForce Now Alliance basically is us creating a server architecture, developing all the necessary software, and partnering with telcos around the world who can't wait to put this service on their 5G networks. The 5G networks or their Wi-Fi networks or their broadband networks, they can't wait to put additional services on top of it. And so these alliances are all over the world. They could be in countries all over the place. Today we're announcing 2 big ones. We're announcing today that the first 2 alliance partners for GeForce Alliance is SoftBank in Japan and LG U+ in Korea, 2 of the major gaming markets. I want to thank you for your support. Our strategy is to put these alliances, set them up in countries all over the world. And they would have data centers, multiple data centers, with GeForce Now servers, and we will host a service and maintain the service for everybody. And the first step, therefore, is to create the server. We call it the RTX server. This RTX server is super dense. It's super dense. 40 GPUs and 8U. 40 of our state-of-the-art GPUs and 8U. You can virtualize it, and as a result of virtualizing it, you can share it with 320 different concurrent users. It's optimized end-to-end, so you could use it for the entire cloud gaming GeForce Now service. You could use it for rendering. You could use it for Omniverse. But that alone is not enough, and it turns out the reason for that is because storage and networking is a really complicated problem. Once you get the data on the server, we can stream it and we can compute it, and we understand that problem super well. But it turns out the entire infrastructure with hundreds of thousands of gamers all playing at the same time, essentially running the supercomputer in real time, the interconnects all become bottlenecks. Everything becomes an issue. And so we decided to create a pod. We created a pod that can scale up to 32 of these RTX servers, and within 10 racks, we can support 1,280 GPUs. It's all connected with high-speed Mellanox InfiniBand, and we can therefore support 10,000 concurrent gamers at the same time. And this is what it looks like. This is one pod. This is one pod. And our alliance partners would install these pods, and basically within a week, they should be up and running, and the service is ready to go. And whether it's all the different countries in Southeast Asia or Eastern Europe, where a big part of the market for gamers are emerging, we could set these things up and work with the telcos as an alliance partner and bring GeForce Now service to all of them as quickly as possible. These servers can now support 3 basic use cases. The first chapter ends here, and it's about the fact that graphics is both, number one, going to go to the next level. It's going to also go into the data center. And data center graphics requires a brand new architecture, and this architecture already supports 3 use cases, and we have others to come that I'll share with you in the future. Our engineers have been working on something really cool, and so let me play it for you now. Ladies and gentlemen, everything you see is in real time. What do you guys think? Another round of applause for the engineers and the creative artists at NVIDIA. Very few technology companies get to sit at the intersection of art and science, and it's such a great pleasure to be here. And to be able to focus on doing work like this and to bring joy to so many people. It's such a creative process, and it just blows my mind every single year when they keep raising it to another level. NVIDIA is the ILM of computer graphics, real-time computer graphics, and you can really see it here. Chapter 2. Chapter 2 is about AI and HPC. As I mentioned today, we're going to talk in 3 chapters. The first chapter is computer graphics. Now we're going to switch gears and talk about AI and HPC. If you look at AI and HPC, we've been talking about deep learning for some time. And deep learning is a new algorithm, new type of algorithm, a new great breakthrough as part of machine learning, which is used for natural language understanding and computer vision, which largely builds up AI. Now, underneath AI, there's a whole bunch of other stuff, like robotics and such. But in the areas that we've been talking about, this is a taxonomy, if you will. Data science is the fastest growing field of computer science today. It is the most sought after job. It is the most oversubscribed course in leading universities, whether it's Berkeley or Stanford or CMU or NYU. It is so oversubscribed, and the reason for that is this. It has become, because of several different factors, it has become the 4th pillar of the scientific method. Theoretical, of course, the Einstein method, the thought experiment, the experimental method, Newtonian physics through experimentation, simulation methods, today's scientists using it for molecular dynamics and such. And now we have a data-driven data science method. And it's made possible because of 3 factors. An enormous amount of data that we can now collect, sensors everywhere, digital everything, phones everywhere, cameras everywhere. We can now have great sensors collect a great amount of information, customers clicking on your websites, customers clicking on your apps. All of that creates data. The second is breakthroughs in machine learning algorithms, whether it's deep learning or machine learning, and the approaches that has emerged recently. And then lastly, computation. And we've been fortunate to have been a big part of advancing and accelerating the computation that makes all of this possible. These 3 factors continuously feed on each other, and then now data science is a pillar of the scientific methods that allows us to solve problems that were previously impossible. We're solving problems that were just previously impossible. Now, when we talk about data science, when we talk about deep learning, we talk about machine learning and AI, I wanted today to frame it for you. The pipeline to workflow starts with data. And there's a stage of the first ingesting of data, the bringing in of data, called data analytics. Then it goes, and from data analytics, your goal is to take data and join it from a whole bunch of data lakes, create what is called a data frame. From that data frame, tabular data, the rows are all of the instances, if you will, and all of the columns are the features. All the columns are its features. The features could be where you live, what your preferences are for movies. It connects with all kinds of things, okay? And so all of the features that you might want to learn from, that's called feature engineering. You take all of this data in, you do all of this munging and wrangling, and what comes out of it, this gigantic table. And that gigantic table could be anywhere from gigabytes large to terabytes large. Could you imagine a spreadsheet that's terabytes large? First of all, it wouldn't load on a normal computer, not to mention what would you do with it at all. And so you do that data wrangling, you do all of that processing, and analytics, what comes out of it is engineered features with a large amount of data that is now in a data set that you can now use for predictive analytics to learn from that data set. And that is what we call AI. Some people call it AI, some people call it machine learning, some people call it deep learning. Depending on the field of science that you're in, if you're in image recognition, of course, you would just use camera inputs. If you're trying to understand something related to disease, the areas of the data source could come from a whole lot of places, including genomics, could be medical imaging, it could even be your family history. From that, you run it through frameworks, and those frameworks ultimately gives you a model, that predictive model. That predictive model, once verified, allows you to now predict the next outcome from other input. So the new input comes, you can now predict the future. We call that prediction process inference. So data analytics, machine learning or AI or deep learning, and then inference. Okay? There's some words that we use, and for some of the people in the audience who are kind of new to data science, this is such an important field, I think it's worthwhile for everybody to understand it. And the words that you hear are things like this. CSV, comma separated values, Parquet. Park is a file format that came out of Parquet. It's a columnar database. Notice the features that are in columns. It's a much faster way of reading it. Hadoop, distributed file system. It is the beginning of big data, the ability to use a large data center, distribute files all over it, and use it for one large compute engine. ETL, extract, transform, and load. Basically, the data analytics process. Pandas, a data analytics program, set of libraries. Basically, the spreadsheet of big data, or the spreadsheet of data analytics and machine learning. Spark for a large data center. Graph analytics, you hear TensorFlow, PyTorch, MXNet, Scikit-learn, XGBoost. These are all frameworks for machine learning or deep learning. And then on the inference side, you have TensorFlow serving, you have Onyx, and you have SageMaker Neo. These are some of the most important and most popular large scale-out inference service and backends. And so these are the words that are going to come up over and over again. And I just wanted to place it on a graph for you so you have a feeling for how all this stuff works. Now, our words, the words that I use that talks about these areas, QIO, it is about vectorizing and massively parallelizing the input, the loading of the IO. Really complicated problem. And you take it from disk, you put it into system memory. It is now in memory in the right formats. And the format is in the format of Apache Arrow. cuDF is a data frame. It is largely compatible with Pandas, except it's GPU accelerated. cuGraph, graph analytics. cuDNN, basically NVIDIA's deep learning API that got this whole revolution going. cuML, which is our family of machine learning algorithms from random forest and decision trees and, k-nearest and k-means and regression algorithms. TensorRT, our optimizing compiler that takes the output of this, which is a model, and compile it down to a target where there's a little tiny computer or a giant supercomputer or a cloud computer, and our inference server that runs on top of Kubernetes called TensorRT Inference Server allows us to now run it in a hyperscale data center and make it possible for millions of people to be doing inferencing at the same time. That's exhausting. It was exhausting to say. It must be exhausting to listen to. All right? If that wasn't hard enough as it is, this is what it looks like when you look at it as an ecosystem. It turns out building a great chip is a nice beginning, but it turns out it's useless until the world's developers and users could take advantage of it. And that's why it's so important for us to work with the ecosystem. NVIDIA is an open platform company. We create all these libraries in a way so that it's software defined and integratable into modern systems. It runs on 3 computing platforms: personal workstations, servers, and cloud. This is the way computing is consumed today. If you're not in all of that, you're nowhere. The next is the system software stack on top. CUDA, and this subset of CUDA today, for this chapter, AI and HPC, we call CUDA-X AI. It has data analytics, has graph analytics, machine learning, deep learning for training, and deep learning for inference. And it has to go out into services to the world, to the developers, in frameworks, in cloud services, and then to be deployed in cloud platforms. And this is the ecosystem at large. Today, it turned out we have a ton of announcements. And I just wanted to put all of the announcements into one slide. So the first announcement is that we now automatically do the mixed precision necessary for our Tensor Core architecture, which is NVIDIA's new AI architecture for GPUs. Our Tensor Core is now optimized automatically for support in TensorFlow, in PyTorch, and MXNet. It turns out that precision is a very complicated problem. There are range issues, there are precision issues. Sometimes you could do it in FP16, sometimes you can't. Sometimes you could do it in Int8, sometimes you can't. You've just got to find out when you can and when you can't. Well, it turns out that compiling problem is a very complicated problem, especially since you have to wait a week and the answer comes back and off by a little tiny bit. These convergence problems are just historically challenging for high-performance computing. Well, Tensor Core is now optimized automatically for these frameworks, and you get the X-factor speed-ups automatically. You do nothing. Number one announcement. Number two announcement is Databricks, started by Matej Zaharie. Matej, I love you. All right, so Matej, who was the founder of Spark when he was back at Berkeley, started a company called Databricks, and they have a machine learning and AI platform that is up in the cloud. It's really popular, super successful company. They have now incorporated and accelerated Rapids, which is the data analytics and the machine learning part of our framework, of our API, into their platform. Google Cloud now has Rapids acceleration. Microsoft today announced that they have Rapids acceleration for Azure machine learning. And then Accenture announced that we're partnering together. They're one of the world's leading professional services company. And Mike Sutcliffe was so visionary to lean into data analytics and AI years ago. They're just doing fantastically, and it's great to partner with them because we now have Rapids and our CUDA-X API and platform integrated into their services. And they're seeing great results from that. They serve 3/4 of the world's top 500 Fortune companies, top 500 companies. And so it's really great to partner with Accenture. Also announcing today that Onyx Runtime is integrated natively with NVIDIA Tensor RT. So all of that today. All so that you can accelerate all of these frameworks and all these AI production systems and development systems so that your productivity could be as great as possible. So I want to thank all of the engineers and all the partners for making this possible. Thank you. The question is, what happens to all this stuff? You know, we look at these things and they're CNNs, and the industry is benchmarking RN50, and it's a little bit like benchmarking Quake, and it's now at 974 frames per second, and we're benchmarking RN50, and we're focused on CNNs, and yet all of this is about ultimately creating services that are incredible and do incredible things. One of the areas where, in the end, we're trying to lead to is this idea of an AI conversational agent. That when you pick up your phone or you're talking to a speaker, a microphone, somehow that AI service is super smart. It's super smart. It somehow figures out how to, when you're talking to it, it's got to do the necessary noise processing, speech recognition. It has to understand your language and convert it to the language that it wants to do processing in. It has to make a recommendation. Maybe it has to do a search. Maybe it has to answer a question. And that question could come back with another question. That answer could come back with another question, which is you could maybe upload an image. And now it has to upload an image. It has to recognize the image. It has to come back maybe with an answer, maybe with another question. And this conversational back and forth with an AI agent has to be fast. And it has to be really natural. If you take a look at the number of neural networks that's involved in the future, it's actually quite large. People think there's one AI somehow running in the cloud. Is just not true. It's like any other software program. These are all models that are sitting in containers, and they're running all over the data center. And at the end of each container, you're sending an output through a REST API to another container running in Kubernetes or something like that on another server. And these containers, services, are sending inputs and outputs to each other. And it's just one program, one service. And it connects all of these different models. It is the reason why people say that east and west data traffic in a data center is exploding. And the reason for that is because machines are talking to machines a lot more than we're talking to the machines. All of these neural networks are talking to each other across containers, across servers. Does that make sense? This is the future. And these models are going to get chained together. And for conversational type models, it is very likely that latency will ultimately define the quality of service. And therefore, we have to process it incredibly fast. Here's the challenge. It's not one network. There are species of networks. There are different network types, and there are different species of them, and every data center's got a different one. And the reason for that is because they've architected it all differently. And some of them, int 8 works. Some of them, int 8 works sometimes, and FP16's got to work the rest of the time. FP16 always works for images. And sometimes, you have to punt all the way back to FP32. Sometimes, the whole network runs on FP32 because that's all the time you've got to optimize it. Sometimes after optimization, there's only so much precision you're afford to lose, and so you've got to mix precision. And sometimes it's good enough. You might even be able to use 4-bit integer sometimes. So this data center is heterogeneous in the number of the types of models it runs, and it has to be heterogeneous in the type of precision that it runs, and it runs across a whole bunch of servers that are connected together. This is the future, the near future of AI in the cloud. There's somebody that I've invited who's going to show you something that's really, really, really cool. Gohan, he's a good friend. Thank you very much for coming here.
My pleasure.
Show us something amazing.
Cool. So what I'd like to show you today is the Bing app. It's running on my phone right here. And for this demo, I'm just going to be a regular Bing user. I'm just going to use this app like a regular user would. And I've been thinking about redecorating a couple of rooms in my house. So I want to kind of change the look and feel a little bit. I want to kind of make them, freshen them up a little bit. And I've learned that one way in which I can do this is by changing the lighting in the room. But as a user, I don't know much about lighting, so I'm going to use the app to help me out here. So the app has 3 icons, 3 buttons in the middle. There's a camera button on the left, search by image. There's a text button in the middle. And I'm going to use the microphone button here on the right. And I'm just going to ask it about lighting in different rooms in the house. So the first query goes like this. Let's try it. What are the different types of lighting for the kitchen?
According to steelandhome.org, as far as general lighting in a kitchen, there are 3 main types: surface, recessed, and pendant fixtures.
I'm going to call out 3 things that just happened.
This is amazing. What just happened, so of course you're going to explain it more deeply, but for the audience very quickly, what just happened is this. Your service recognized your speech. It figured out what you were trying to say. It went to find the information. Yep. It then presented back to you in 2 ways. One way is to say it back to you, so it has to do speech synthesis. Yep. And then the other way, it had to compose this page to present the information to you. And so look what just happened, okay? Speech in, what came out was visual and verbal. All right? Several different models all happened, not to mention the search algorithm behind it. All right, go.
That's exactly right. And so I just wanted to highlight exactly the components you said. But this card up here up top, we call it the intelligent answers. And that goes through the top documents that came back for that search query, reasons over them real time in response to the query, and it finds the best passage from all those documents, all those sentences that answers the question that was asked. And within that passage, it highlights in bold the specific phrase that we think is the answer. Right? So that worked for the kitchen. And as a user now, I want to learn about other rooms. Maybe I'm looking at a living room. So let me try asking about a living room instead. What are the different types of lighting for the living room?
According to thespruce.com, living rooms require 3 types of lighting: ambient, task, and accent.
And Guhan, I got to tell you, I just realized something as you asked. I'm missing one of those 3 lightings in my house. That's why my eye's going bad. Honey, our task lighting is in trouble. We have plenty of ambient light, and the accent light's working great.
Well, I actually have the opposite problem, so I'll find out more about accent lights in just a second. But the thing I wanted to highlight here is it's a very consistent experience. Again, for this query, there was speech in. The intelligent answers card gives me the answer, and the speech readout, the text-to-speech service, is reading out the speech. But the other thing that I wanted to call out is there's a little embedded image in the answer, and as a user, I'm visually drawn to that. I want to learn more about images, and I actually don't have accent lights in this room, so I'm going to learn more about accent lights. Show me images of accent lighting for the living room.
I pulled up some images for you.
So here, you see it has a whole bunch of images of living rooms with accent lights. But I like one of these. I'm going to pick the first one, and I can actually look at it in more detail. And up top there, there's a button that we call the visual search button. And when I click on it, not only can I see the whole image, but I can actually select different parts of the image and find some portions of the image that maybe are more interesting. So in this case,
wow, that's cool.
I'm just going to center in on maybe the lamp that I'm looking at. And not only as I do that, does it find images that are similar to the lamp I've selected, but now there's this shopping tab. And as a user, I can click on it, and I can buy lamps that happen to look similar to the area that I selected in this random picture from the internet.
That's pretty awesome. Okay.
And that is object detection that's also happening in real time. As I change the selection, this is running in real time. And to Jensen's earlier point, the latencies for these things are super critical. If this takes 3 seconds to refresh, no user's going to use it. Right? So our latency budgets for these models are super tight, and that is kind of a very key aspect of the experience. So Jensen, what I hope I showed you is an experience here that sort of brings together 4 very different types of models. So there was speech recognition, there was the intelligent answers, there was the text-to-speech readout, and there's object detection. Right? But to me, as the user, it was just one immersive, fluid experience. As a user, I didn't have to worry about all the AI that happened in the back end. And that's, to me, the best kind of AI. It just works. But of course, in this room, we're all technologists. We know how hard it is to get these things to work seamlessly. And for the Bing app, which, by the way, you can try. It's available on iOS and Android devices today. For the Bing app, we relied and we used the Azure N-Series VMs, which rely on NVIDIA GPUs.
That's awesome. Thank you. Ladies and gentlemen, Guhan Siranarayanan. I like saying your name. All right. That is an example of extreme inference, extreme inferencing. That pipeline is complicated. It went through a lot of different models. And imagine hundreds of millions of people doing it this way. Well, we're working with the industry at large to accelerate inference and to be able to deploy services. TensorRT has been downloaded so many times now, 300,000 times, 6 times growth in just 1 year. And some of the best services, some of the most popular services that you guys know of, and a whole bunch of them that I didn't list here, are now using and being accelerated by NVIDIA GPUs as a result of TensorRT. Voice search and image search and recommendation systems and assistants and news feeds and translation and e-commerce, all of these things have modules of AI models in it, and they're accelerated by NVIDIA GPUs. One of my favorite uses of inference is medical imaging. There are 100,000 radiologists in here just in the United States alone. We also have the best trained radiologists in the world. They used to be able to study, they used to be able to look at a study and study it for 20 minutes. Now they barely have 4 minutes to study the same thing. The pressure on them is incredible. It is the largest operation in a hospital, and yet early detection is the best way to stop something before it gets worse. And so the question is, how do we apply deep learning to enable all of these radiologists and augment them so that when they're doing their work, there's an assistant sitting next to them, helping them along. Maybe at the end of the day, they're doing QA. And meanwhile, recognizing that there is no way that one institution, one group can possibly train all of the neural networks for all of these rare diseases. Many of them happen very infrequently, and so many of them have experts and specialists in the field. Well, so what we decided to do is this. We decided, instead of being the one company to solve it all, we would help them create tools and put it in the hands of radiologists all over the world. Give them AI tools, and then give them an AI infrastructure. Make it super easy for them to share work among themselves, but we've got to give them a starting point. So we started with pre-trained models. We have 13 pre-trained models up in NGC. They're incredibly well done. We worked with radiologists in research hospitals, and we dedicated ourselves to make amazing pre-trained models. The second thing is we have a tool that basically is an AI that's going to create AIs. And it helps with the assistance of essentially annotating, doing the laborious work of annotation. And then we can do transfer learning. We fine-tune these models with the data that you provide. So you download a pre-trained model, you annotate your data, you then fine-tune that model, and then we compile that into a model that you can use. And then we make it possible for you to deploy it easily, the entire framework I described earlier. This entire process, end-to-end, is easy peasy. And it's being used all over, easy peasy. That's very technical. It's being used all over the world now. We're so happy that MGH, NIH, OSU, some of the leading DKFZ, some of the world's leading research hospitals are now using it for assistance of annotation or the deployment of the model or integrating it into their own tools. All of this is open sourced and will make it available for researchers all over the world. So we call this the Clara AI Toolkit, and you can come and download it. All right? Thank you. Data science is the new HPC challenge. HPC, using computers, very large computers, to solve very difficult problems. Because the data is so large, because the computation necessary is so great, this is the new HPC challenge. And just to show you one of the examples, and there's so many examples during the talks at GTC, I think Walmart's going to give a great talk. I can't imagine. The world's largest company surely has the world's largest data, and they have millions of SKUs simultaneously that they're managing and forecasting, and they have stores all over the place. And they have to find the exact right level of inventory for every single SKU to arrive at exactly the right store for exactly the right time, because during every season's a little bit differently. Maybe there's a run on something special like bananas. You know, different types of products have different seasons and demands, and they have to monitor and they have to ingest all of that data and use it to train a machine learning model so that they can predict inventory faster. Well, because of our platform, they could do it now practically in real time. You should go listen to their talk. There's so many other talks here related to using NVIDIA's machine learning platform to accelerate data analytics and data science. Well, we have somebody here, Aaron Williams. Aaron, are you here? I can't see you.
Right here, Jensen.
All right, Aaron, welcome to GTC.
Thank you, sir.
Aaron has been working with Charter, one of the world's largest cable operators, to apply data science to solve their problem. And so why don't we let's go to your demo. Let's take a look at it.
Yeah, sure. This is a really exciting real-world example of putting AI to work for data scientists. As Jensen was saying, we're working with a network operator that has 25 million subscribers connecting to 500,000 LTE towers and Wi-Fi networks. Those connections they're really the lifeblood of this business, and that data is super important. So what we're going to show is how we can put AI to work to help the network operator make smarter decisions using these predictive algorithms.
Now, the decision, just to go to the end and work backwards,
sure.
The decision they're trying to do is they're trying to figure out where to place Wi-Fi access points to offload from the cellular traffic so that they could provide the best possible quality of service, and then, of course, and to increase the capacity for their company. But you don't want to place it randomly everywhere.
They're adding 10,000 of these Wi-Fi access points per month. That is a big decision. They got to decide where to put them. And they can save a lot of time and money if they put them in the right place. And so what we're going to do is help them predict where to put those Wi-Fi access points.
Okay, that's awesome. And so the first step, of course, is we have to take the data in. We have to do basically ETL, extract, transform, and load. We have to do basically data analytics.
And this is a lot of data, Jensen. It's a terabyte of data per day that they've got coming in. Now, when you're talking about data scales that big...
Well, usually, you know what people do when they have a terabyte of data that comes in every single day? Ignore it.
That's right. That's right.
Yeah, that's right. Because tomorrow it's going to come back again.
That's right.
And you'll ignore that one too. Because it'll come back next week.
That's right.
That's the beautiful thing about recurring data. All right, but obviously they would like to use this data.
Yeah, this terabyte of data.
Their business.
Yeah, this terabyte of data is not also a really clean set of data. Of course, it's coming in from multiple different data sources. They've made some acquisitions over the years. That means they've got gold mines of data that they all need to combine into a single taxonomy.
Now, the industry calls it, give it a great name. It's called a data lake.
Yeah,
right?
well.
And the data lake's got all these different formats. It's all messy data. And some people call it dark data because you're never going to look at it again.
Yeah, to your point, what they were doing before was spending 8 days to be able to transform that data into a usable set of data. And this was all done manually. We had data scientists, dozens of data scientists spending their time transforming this data to make it usable.
So let me see if I understand. You got a terabyte of data coming in every day. It takes you 8 days to process 1 terabyte of data.
Yeah, to make it usable.
Uh-huh.
So guess what?
Pretty soon you're going to be infinitely behind.
Yeah, guess how many days of data we're not getting watched, right? So here's what we've got. On the left-hand side here, you can see this sort of incoming data. This is the complexity of the data that they had coming into the system. Dozens of different sources, all kinds of different formats. We're going to use a product called Datalog, a really awesome product for being able to transform that data into usable data. The first step in that process is...
By the way, Datalog is really fantastic. They so this is Tim's company. I think Tim is watching. Tim, good job. Go ahead, Aaron.
Yeah, they are great.
Fire away.
So what we're going to do first is define an ontology. This is basically just a knowledge graph that helps us transform what the data is that we have to the data is that we want. And so we've defined here the different data sets that we want. Each of these data sets, then, we can use AI to be able to transform the data we have into this data set that we want.
Yeah, and now what's really amazing, what Aaron just said is this. Just imagine. So you have basically data, let's say you have data sets coming from 10 different places. It's the same data. It's about the same thing, but the format's all different. The names that they use, the labels that they use, the columns they use, the features, the names they use for the features are different, but just a little different. Just a little different. You know, maybe your name's spelled just a little differently. If you and I were to look at the database, we would be able to tell that this column and this row is the same thing. But to a computer program, they're basically exactly different. Now, what we need to do is we need to have these AIs that are basically looking at all of this data as we're taking it in and realize that, you know what? That JEN-SEN and JEN-HSUN is the same person. It's the same person. It's okay.
Yeah.
Put them all in there.
Let's go look at actually what it looks like when we train these models. So this is an example of a model that we've trained for being able to predict these values. You can see that the different values that were coming in on the left-hand side, the values that we were predicting on the top there. You can see how successful this model is at being able to determine the different kinds of data coming in with the different data that we need in our ontology.
You were off by 2.
Yeah, well, so this is interesting though, right? Because sometimes you'll confuse an IP address for a different kind of data. Sometimes these things they look the same sometimes. The good news is we've trained this model so well that it's 99.9% accurate, which is much better than investing the 8 days worth of data scientist time to be able to produce those same results.
No, it would take days to do this by hand.
That's right. We want to automate it.
Days to do this by hand, right?
Yeah.
Not to mention just the computation of loading it and reformatting it and joining it and grouping by this and doing the SQL processing that you guys are familiar with, doing the SQL processing on it. It takes so much energy to do it. Eventually, you have this thing called a data frame. That data frame then comes into another amazing product this amazing product is from a company called Omnisci, isn't it right?
I've heard of that company.
Yeah.
This is a company called
This-
Omnisci.
that you and Todd started, and Todd, is Todd out in the audience?
Todd's right here.
You know, Todd, good job, man. Good job. So Todd realized the importance of GPU-accelerated data science, quite frankly, almost before everybody, practically, not just momentarily before me. Okay? And then he came and told me, then I realized, hold on a second, this is a high-performance computing problem. And so we've been working together for some time. Omnisci, you guys are doing amazing work. Now talk to me. Now here's the data frame.
Yeah, so now we've got all this clean data, right? Now we want to actually put it to work. So we're going to bring it into Omnisci. Omnisci is a SQL database that is built to run on GPUs, and it also has a visualization engine. Let's cut to the dashboard so we can see what that looks like. Now, this is 500 million rows of that network access data that we were looking at before. This covers 215,000 access points.
You got to let that moment sink in. You guys know what a spreadsheet with 500 million rows look like? I know.
This is 200.
I've never seen one that big.
Yeah. 215,000 access points across the entire US. On the left-hand side there, you can see this really nice heat map showing where those access points are and where they're being used the most. Let's zoom into Ohio, actually, just because you can see how easy it is to zoom in and get a much clearer picture of a specific part of your data. So now, look how we've zoomed in, and now we're seeing the detail of what's happening in the state of Ohio. I'm going to go use the time chart here in the middle to zoom in not just by location, but now by time as well. See how when we changed to the chart at the bottom there, now we're seeing hourly results at the top. And as we scrub over to the right, we're seeing all of the charts changing in real time to show us what happens at different time frames in that data set. Now, Jensen, this is the cool part, because what's actually happening behind the scenes here, we're running hundreds of SQL queries against that database. There is no way you could do this on CPUs. It's only possible because we've architected to run on GPUs.
It was like yesterday morning that SQL was a batch job.
That's right.
You guys are now watching this in real time.
And
this is craziness.
This is no indexing, no aggregation. This is 500 million rows of raw data.
Are you guys getting this? SQL used to be something you would run with Hadoop, and it would be a batch job.
That's right. That's right.
You know, now you're doing this interactively, and you're visualizing it in real time. It's incredible.
Now, this is just the first step, though, Jensen, because now we're actually seeing the historical data. Let's get to the predictions. Let's get in our time machine and start to see what's happening in the future. We're going to do that using a Jupyter Notebook. So we'll switch over to the Jupyter Notebook now. And this is an interface that all data scientists are familiar with. It's Python. We're going to actually, in the first step there on the left, we're going to actually get a pointer to that data sitting in the Omnisci memory, in GPU memory. We're going to use that pointer to do the feature engineering that you talked about before. And on the right-hand side, we're going to run our XGBoost to do the training, to do our machine learning. Very familiar toolkit here of tools. That pointer is exactly a pandas interface, which is what you're looking for if you're a data scientist, right? So these tools give us those predictions. Once we get those predictions, we're going to push them back into Omnisci so that we can make a complete visualization of what that looks like.
Did you guys just see this? So first step is data analytics. And within data analytics, you could use Omnisci to visualize it. Just take a look at the data so you can get a feeling for it. Then once you do that, you've done the feature engineering, you take that into that data frame, you put that into XGBoost. That XGBoost is your machine learning algorithm. That machine learning algorithm is going to take the previously collected information and all of the features, and it's going to learn a model that predicts the future from those features, okay? Predict the future from those features, and it's going to come up with a new model.
And let's not forget about Rapids. Rapids is an important piece of all this that ties it all together, right? So we're using that here with these data frames that you talked about to be able to do this kind of prediction. Okay, we pushed the data back into Omnisci. Let's go back to that dashboard now so we can see what that looks like. You'll see on the time chart now, we have this dotted line that goes into the future. So as we scrub through, again, we see that same interactive experience of scrubbing through the data, and now we're seeing predicted results for where we think the usage is going to be across the state of Ohio. And you can see the same sort of interface, the same interactivity that you get now using these predicted results coming from Rapids using cuDF.
And guys, you just saw in just a really quick moment here predictive analytics in practice from the beginning to the end. And if we could accelerate everything, and what Aaron was saying was it's called Rapids. Rapids is the machine learning framework, the data analytics, the data science framework that we open sourced. Underneath it is a whole bunch of engines. Those engines are basically CUDA-X. And Rapids is now open sourced. And the important thing is you see down here, this is where I grew up, Oneida, Kentucky. And there's no traffic there at all. I think, here, somebody type in Oneida, Kentucky. Let's just, Oneida, Kentucky. Let's see. Just one access point. Come on. Give us one access point. That's it. That's where I grew up. One intersection. I'm not kidding. Not kidding. All right, so everybody's still baffled. They're going, that can't be right. That can't be right. That is right. So that's where I came to, United States. And so here we saw the entire platform. How long did it take before, and how long does it take now?
Right, so we were talking about 8 days before, just to get to a point where we had some data we could do something interesting with, and then it was taking us hours to do queries after that, right? Now we're talking about 4 minutes to be able to get data the way we want it. That's near real time. And then what you're seeing here is absolutely interactive engagement with that data. So it's just a completely different paradigm of what's possible with this data.
So here we go. Data scientists, the most sought after professional in the world today. They're sought after in every single industry, in every single company. And then once they get them, they make them sit 8 days as they work on data that is 8 days old, 7 days old. Okay? And so that makes no sense. What we want to do is we want to accelerate their work, give them the instrument of their science, give them the instrument, the tool of their science, so that they could do their life's work, and to do their life's work as quickly as possible. Ladies and gentlemen, Aaron Williams.
Thanks, Jensen.
Todd, you guys got something good going. Okay, so what we need to do is we need to build high-performance computers for this whole new area called data science. You know, design automation, computer-aided design, styling, media and entertainment, climate simulation, energy discovery, molecular dynamics. They all have high-performance computers. They all have workstations that the engineers and scientists and researchers work on. Well, there's a whole field now. It's called data scientists. There are 3 million of them around the world. 3 million of them around the world. As I mentioned, it is oversubscribed in every single class. We taught 100,000 data scientists ourselves last year. Our program is called Deep Learning Institute. We taught 100,000 ourselves. There are classes all over the web. This is an area that is hot and brimming with excitement. And the reason for that is because the 3 things that I mentioned that came together, the availability of data, the machine learning algorithms, and high-performance computing has made it possible for us now to use this as the 4th pillar of scientific discovery. We think there needs to be a new type of computer built. And so we decided that the workstation has to be re-engineered, a new type of workstation with very, very fast storage, very, very fast I/O. Really fast computation with very fast memories. This type of architecture, a workstation for data scientists, is really complicated to build. In fact, just us building it, installing and building the software and tuning the whole computer to deliver the performance is not easy. We're basically taking what otherwise is a high-performance computing data center IT team and shrink it into one box and make it possible for us to ship these like appliances all over the world. We came to this idea because some of the world's leading researchers were building it themselves. And some of the companies at the forefront of AI were building these machines themselves. And they were building it right in front of us, and they asked us, how do we make this easier? It came to us because customers were asking for it. And so we decided to build the workstation for data scientists, and this is the performance. Look at this. This box, if you were to run it the old way, it would be the blue bar, and you run it with one RTX 8000 or 2 RTX 8000, and now you basically have a performance similar to what Aaron was showing you. The industry is so excited about this because the demand is just right there. All of the world's leading computer makers have joined us in this endeavor, and today we're announcing a brand new family of workstations. We call it a data science workstation, and it's going to be available from the world's leading computer makers, Dell, HP, Lenovo, and all of our partners. I want to thank you for joining us. This is a good way to get going for one data scientist. However, the jobs, many of the jobs are so big, it's impossible to fit on one computer. And that's why we say that data science is the new HPC. It's the new HPC. Now, before I go into HPC, let me give you a taxonomy also of how supercomputers and high-performance computers are created. This chart, by the way, this is JHH mathematics. Inside NVIDIA, that's called CEO math. It is not accurate, but it's right. Are you guys following me? It's not accurate because if you nitpick it, it's going to be off. But if you study it, you go, darn it, I think he's dead on. Okay? All right, it goes like this. Basically, high-performance computers are built in for two fundamental applications. On the one hand, you want to build something with capacity. Okay? With capacity. This is this side. The other way, this vertical side, capacity, capability. Capability is building a computer. You have a computer, the largest possible computer, so that you can run a simulation as fast as possible, or the largest possible simulation you could imagine. A capability machine. That is designed in a way that we call supercomputers. For very few jobs, very, very, very large ones, and you want to get it done as quickly as possible, or you want to do the biggest one you can. The second is called a capacity machine. This capacity machine, otherwise known as hyperscale, uses efficient cost computers, millions of them. And what you want to do is you want to serve millions and millions and hundreds of millions and ideally billions of people with small jobs, with many small jobs. Okay? So the architecture that you create for hyperscale and the architecture you create for supercomputers are not the same. Are not the same. This is called scale out. This is called scale up. This has maybe 1 million nodes at a data center. This has tens of thousands. Supercomputers, what I show here is the compute. It is the computation load. Not the flops, but the flops as in instances, not time. Okay? The number of instances of compute is 1 billion petaflops, for example. 1 billion petaflops where the S is units, not time. And this is hundreds of millions of people concurrently. Data centers of two types. Both are high-performance computing data centers. This is where supercomputers go. Capability machines, scale-up architecture. This is where hyperscale goes. Capacity machines, what people call scale-out architecture. Are we okay? All right, here's where data science goes. Data science goes right here. These are tough problems to solve. Engineers love problems here. Engineers love problems here. These ones are hard because it's not quite this or that. It's not quite this or that. And the reason why it's not quite this or that is because in the case of data science, notice the amount of data is gigantic, and if you want to train a network or if you want to do data analytics on it, you do computation for days. Those are characteristics of a supercomputer. A few people using a large cluster for days, otherwise known as a supercomputer. On the other hand, data scientists is in the millions. We don't have millions of weather simulation experts, or we don't have millions of molecular dynamics scientists. We have millions of data scientists. And so all of a sudden, the concurrency of data science is both large and the computation requirement is also large. Of course, not everybody is the same way. And so we need to have multiple architectures to solve this. This is where DGX goes. We created DGX, which basically takes a supercomputer and we turned it into an appliance. We integrated everything, lots of GPUs. It's a scale-up architecture, 16 Voltas, 16 V100s, 2 petaflops of computing, half a terabyte of high-speed memory, essentially 16 terabytes per second of aggregated bandwidth, and we have 8 Mellanox InfiniBands on here to get the fastest possible access to the network and to storage. This is where DGX2 goes. The next step of our journey is to accelerate hyperscale. To do essentially the same as with DGX, but we have to do it for hyperscale. The software stack is different, the architecture is different, the whole solution stack is different, the go-to-market is different, everything is different about it. It took 2 years longer to do this than that. And you'll see in a second why. And so this is called scale-out acceleration. We're going to accelerate scale-out, and we're going to address the millions of data scientists, engineers to the bottom right of that center bubble. And the solution for that is this GPU we've been making called T4. T4 is the first GPU. Tensor Core is our second generation Tensor Core GPU. It's literally 70 watts. It's the size of a candy bar. It fits into every single of the high volume, most popular data center servers in the world. It can fit in a blade. It fits in a hyperscale server. It fits in an enterprise data center server. 4 T4s gives you about 260 teraflops FP16, so it's a supercomputer essentially, and it comes with Mellanox or Broadcom Ethernet NICs. In the end, the software stack is the complexity, and it basically looks like this. You noticed earlier when I was talking about inference, one container, the output through a REST API goes into another container, and it goes into another container, eventually comes back out, and it recognizes your speech and answers your question. Those are containers. Those are all containers on Kubernetes. What you're seeing here is distributed computing. Notice a whole bunch of users are using a server. Containers are communicating with each other. Data is going back and forth. Over here, a whole bunch of servers, a whole cluster is working together as one compute engine. It's running one job. Okay? Hadoop started it. They used it for, of course, crawling the internet and doing search. Hadoop is a in-disk computation system. In-disk computation system. Uses commodity off the shelf. Was a brilliant strategy, brilliant architecture. Basically, you could take terabytes and terabytes and terabytes, 100 terabytes of data, internet, put it into your disks, and stream it out to the disk, doing map and then reduce. Okay? Basically, Hadoop is HDFS file system, the Yarn distributed scheduling system, and map-reduce compute engine. That revolutionized big data. However, because most of the data is sitting in disk, the computation was slow, and then Spark came along. And Spark came along and read everything into memory. So now instead of small amounts of memory on all these servers, now you have big amounts of memory, and it loads everything into memory, and now it could interact on it and iterate on it in real time. First time people were able to do basically interactive SQL searches, SQL processing in a data center. However, the story goes, eventually, Moore's Law started to slow. And the data kept getting bigger and bigger and bigger. And now we have to accelerate that. And that's where Rapids came. Rapids is an effort that started about 6 years ago, and the industry has been working together on that, and it came in several different layers. The first layer is to completely re-engineer the memory system. The in-memory architecture is now called Apache Arrow. The second part of it is a scheduling system called Dask. And the third, the new compute engine called Rapids. And Aaron was talking about that. That's integrated into the work that they're doing. These three stacks, Hadoop for disk-oriented, low-cost systems, built on top of that, Spark on top of HDFS, built another version of it, which is the GPU accelerated version of it, called now Rapids. And you saw earlier, Rapids is seeing great success. It's been adopted into Microsoft Azure. It's been adopted into Google Cloud. It's been used all over the place. It's just fantastic. And this is how we're going to accelerate, basically, your distributed computing capability. The one thing that you can notice about this is that between these containers is a lot of traffic that's going back and forth, what the industry calls east and west networking traffic. The east and west networking traffic is going up exponentially. What the industry calls north and south, basically data center to cloud, is not growing exponentially. And the reason for that is because the number of people in the world is not growing exponentially. It's growing, but not exponentially. The amount of traffic inside that data center is growing exponentially. Second, when we create these large distributed computing systems, the broadcast, the collecting, the reducing, all of those primitives necessary to do distributed computing is causing an enormous amount of traffic inside. So it turns out, in the future, the way you design a data center is going to change. Instead of a whole bunch of compute nodes that are connected essentially by networking, the networking and the compute will become one continuous computing fabric. The network is going to become really, really important. And that's one of the reasons why recently we announced that we're acquiring Mellanox. And let me do this. Let's introduce the CEO of Mellanox, E.L. Waldman, please. Ladies and gentlemen, a visionary, a giant in the industry, and pretty big guy.
Thank you for the introduction, Jensen. Great being
here. So EL, we've been working together for some time.
Yep.
And we've been working on supercomputers for some time. In fact, I think we've been working on it for about a dozen years. You've been working on it for almost 20 years.
Yes.
And so we've been building supercomputers together. And what are the trends that you're seeing in the world of high-performance computing?
Right, so I think like Jensen said, we're seeing a great growth in data, an exponential growth, and we also are starting to see that the old program of program-centric data center is changing into data-centric data center, which basically means the data will flow and create the program. Instead of us creating a program using the data will start creating the program using the data itself. And this is things we can work on and actually have very synergistic architecture solutions for the future for the data center.
Mm-hmm. And so, if you take a look at our journey together, we started in supercomputing, and almost all the major supercomputers we worked on, you guys worked on as well, and our engineers worked close hand in hand. And the reason for that is because, when you have all these different compute nodes working together, the synchronization of the information, the sharing of the information into one large simulation is very intensive. Right. But we're seeing the same thing happening now in hyperscale data centers, and we're seeing the same thing happening in enterprises. And what are you guys seeing, and what are the dynamics that's causing that, you think?
Right, so I think if you look at the big hyperscale, one of their big advantage is the compute engine, the supercomputer they have in the data centers worldwide to serve hundreds of millions of people simultaneously. What we help is actually connect the compute to compute and then compute to storage in the most efficient way with the lowest latency and highest scalability. And this is why we increase the productivity, the efficiency of those data centers significantly. Some of the things you showed here is that latency is one of the most important parameters in terms of scalability and then efficiency and productivity, and that's what we do best. We have the lowest latency interconnect on the planet, both on InfiniBand and Ethernet, and we're just improving this now with 200 HDR InfiniBand and also 200 and 400 gigabit Ethernet that we'll continue to develop and have more synergistic products in the future. Yeah, so between the NIC, the switch, the latency of your system is just really incredible. The other thing that you were well ahead at the time was the concept of CPU offload and RDMA, and we also felt the same way. Of course, we didn't call it CPU offload, we call it acceleration. But in a way, you were a network accelerating company all along. Right, so we found out that doing programs is great by the CPU, but then doing very tedious I/O operations by the CPU is very not efficient. So we took this task on Mellanox, and we do it mainly on the endpoints, on the NIC and HCA with InfiniBand. Then what we found out is we can put computing inside the switch, and this is something we've done with NVIDIA Sharp 2. Actually, to accelerate, we have like an AI offload machine, floating point machines inside the switch to increase the efficiency of artificial intelligence programs in the data center. This is something we're working together. I think you have very recent results. I don't know if you've shown this recently, but we are seeing more and more offload we can take away from the CPU and GPU into the network and then synergize this into the whole data center solution for AI.
Yeah, and that's our path forward,
Yep.
to find a way beyond the time when CPU scaling is going to continue to progress. Now that it's slowed down, we have to take as much workload as we can, and of course, moving it into an accelerator is one thing, but moving it into a network is a completely another thing, and we should do both.
Right, and
So-
we will execute on that.
Fantastic.
Thank you.
Thank you,
Great
Yale.
being on
Thank
stage
you.
here.
Thank
Thank
you,
you.
Yale. Ladies and gentlemen, Yale Waldman. Incredible guy. We've got a bunch of Mellanox switches and NICs all over our products. And so now we've created these machines. We've created these machines and these systems. We've got to take them to market. And the market is fragmenting very quickly in the sense that the number of customers that use data analytics and data science is growing so rapidly. It's gone from research to the world's internet companies, what we call hyperscale companies, cloud service providers. It's moving very quickly into supercomputing, physics-inspired neural networks and AI, and it's moving, of course, into enterprise. And we're trying to take these various different kinds of computers to the world. And so we have to, for each one of these markets and each one of these segments, we have to use a different go-to-market. One of the ways we're going to market, we're taking the DGX and basically these AI supercomputing appliances with all the storage and all the switching, which is really complicated, and bringing it to the enterprise. We have a suite of partners that we're working with. Really great partners, DDN, Dell EMC, IBM, NetApp, Pure Storage. They know a ton about storage, and they happen to be working already with all of the people who use a lot of big data. And so partnering with them, creating essentially a pod, and these pods are fully integrated, what the industry calls essentially hyper-converged. You could take all that, you install it literally within a day. We come in, or somebody comes in. I don't come in, but somebody comes in between zero. I was almost going to take credit for it, but I don't think I should. It's awfully heavy. And so you bring it in. Zero to AI is basically in a day, a few hours. And so really fantastic. Work with Arista and Cisco on switches and Mellanox on switches. Together, this represents a large part of the high-performance computing industry, and we now take these capabilities into the enterprise. The second thing is now the larger enterprises. The DGX pods that I just mentioned comes in to the upper left-hand side of that bubble of data science. Now we want to take it into the bottom. Where the top and the bottom goes, the computation is 3 orders of magnitude apart. But yet the market size, the number of engineers, the number of data scientists is also 3 orders of magnitude. Instead of 1,000, now we're talking about 1 million. Instead of thousands, we're talking about millions of people. And so we're going to need a large network of partners to be able to take these architectures, which are relatively complicated, which is only possible really today in the cloud service providers, to bring it out into the world's enterprise, and so that they could set it up easily and to be able to run these workloads as easily as possible. We're announcing today that nearly all of the world's leading computer makers for enterprise has joined us to take this new architecture, this data science server powered by T4s, the CUDA X AI stack, and all of the machine learning frameworks that I've already spoken about to take it to market. And so I want to, if I could ask you guys to congratulate them and thank them for joining our team. Let me show you what these servers look like. So just now you saw what a workstation can do. Now this is a gigantic data set, and this is what it looks like. In the case of this data set, it's several hundred gigabytes large. End to end, it takes 35 minutes to do on a cluster of 10 servers. okay? And on a cluster of 10 servers with one T4 inside, it's almost 0. And so basically, we take it from half an hour end to end to 3 minutes. Barely enough time to get up to get a cup of coffee. Okay, so in the future, you will get, all the data scientists in the world are going to be substantially less caffeinated. We're going to get a lot more work done. Here's an interesting, this is MXNet training using the same distributed servers. And notice it starts to plateau. This is the problem of distributed computing. This is the reason why scale up is better than scale out for some very large simulation jobs. Because by adding more and more servers, notice the return on that investment starts to decline. And the reason for that is because you're spending too much time communicating. And so this is with the fastest Ethernet, and this is with the fastest Ethernet with RDMA, the technology that Mellanox invented, and now it's an industry standard called Rocky. Okay? So this is the reason why networking bandwidth is so important, and why networking offload is so important, and why software integration of the stack is so important. What I see here, what I show here, it looks simple, but the amount of software that goes into making all this possible is really incredible. Well, that's enterprise. If we want to reach a lot of people, and want to reach a lot of people fast, with the single largest compute engine on the planet, there's one way to do it. And it's the only way to do it. Ladies and gentlemen, is the Amazon way to do it. And so if I could just invite Matt Garman, a partner of ours, I've been working together for years. Matt.
How's it going?
Great to have you here.
Thank you.
It's great to have you here. We started working together 7 years ago. You put a Fermi GPU in the cloud.
We did, yes.
What were you thinking? But anyways, Matt put a Fermi GPU in the cloud and opened it up as a GPU as a service.
Yeah.
And that was the first time. And actually, to be honest, when you first did it, I was kind of going, yeah, I don't know where this is going to go.
A lot of people thought that.
Yeah, I'm enthusiastic. I'm happy to sell any GPUs. But it was so cool to see. And then you were the first to launch Volta into the cloud, and then you were the first to launch an 8-instance HGX2 Volta into the cloud, and we've been working together ever since.
We have, that's true.
And so it's great to have you here. You guys have been doing AI in the cloud. You've got this layer called, this service called SageMaker, and it's a fantastic tool. You know, I'm going to hand this to you. You got a couple slides, but can you tell the audience about some of the work that you guys are doing and,
sure.
And the success you guys are
happy to. And so, and I've actually been at Amazon and AWS about 13 years since we started AWS back in 2006. And over that time, you know, really our goal is to develop, and what we've done is develop the most reliable, fastest cloud for anybody out there. And really how we think about that is we want to deliver services across the world for everybody. We want compute services, storage services, we want data analytics services and networking services across 61 availability zones and 20 regions all around the world, and particularly ML services. And that's a lot about what you've been talking here today. And when you think about ML services, one of the things that's really exciting is machine learning is a great fit for the cloud. A lot of our customers, and we have more machine learning is done in AWS in the cloud than anywhere.
That's amazing.
And one of the reasons for that is because a lot of our customers are still trying to figure out, and a lot of these people here are trying to figure out how exactly do you incorporate machine learning into your applications, right? They're still trying to figure out exactly what are the best ways to do it and iterating on that. Well, the cloud is a perfect fit for that. We have customers who come, launch large clusters of P3 servers running Voltas, and they'll run their training applications, and they'll spin them up, and they'll test them, and they see how they go. They spin up lots of computers and lots of servers so they can get the work done quickly, and then they shut it down. They don't pay for any of that infrastructure, and then they go look at their results, they iterate, they try some new algorithms, and then they go spin it up again when they're ready to do it. And in fact, one of the services that we've delivered, as you mentioned, is called SageMaker. SageMaker is an end-to-end, fully managed machine learning service that makes it easy for data scientists, developers, even machine learning experts to easily and scalably launch their machine learning applications in the cloud, all in NVIDIA and EC2 technologies.
Now, what are some of the customers that use your stuff? I mean, and tell the audience about some of the things that they use it for.
Thank you. And yeah, it's with AWS and Amazon, we always start with the customer. That's really kind of where we think about it. And we have thousands and thousands and thousands of customers using ML in the cloud today. I picked up a couple of them here, some well-known customers, and I'll highlight a few of them for you. We have some customers that are actually doing traditional HPC. We have customers like Western Digital, who use P3s and Voltas to look at a wide range of factors from material science properties to magnetic and heat flows and all sorts of things to really improve the quality of their disk drives.
We've got a lot of customers that are using your stuff for seismic processing.
We do. They're doing all sorts of these.
Yeah.
We have, if you look at a different industry, we have Celgene. Celgene is a biopharma company recently bought by Bristol Myers Squibb. And they have AI, and they're looking at a bunch of different drug designs to see what's going to happen fastest. They used to have a cluster on-premise that would run their applications. It took them 2 months to run this complicated application. They moved to the cloud, scaled out, and now they're able to do it in 6 hours.
Wow.
And then there's a couple of Bay Area companies.
2 months to 6 hours. When you say that out loud for a second,
it's amazing.
It's
right?
actually, yeah, shocking.
Yeah, and so think about not just the cost that they're saving, but to your point, the most precious resources, that data scientist time and that ML scientist time, and the iterations that they're able to make are incredible for their business. Yeah. And then many of the top technology companies here in the Bay Area, from Salesforce using it in their Einstein Vision application for their developers, finding image recognition for brands that are online, people like Airbnb making it easier for their hosts to figure out how much they should charge for their property, or even Lyft. Lyft recently announced that they're all in on AWS. Everything that they're running is all on AWS for their 50 million riders per month.
That's amazing.
And they use AI and ML running on P3s and Voltas together with SageMaker to calculate everything from estimating fares to better drop-off and pick-up things to fraud detection in the cloud. It's just a couple of examples.
That's just amazing.
And one of the things, these are all kind of training applications, but many of
my favorite app, Yelp.
Exactly.
It's working great. That's incredible.
Yeah.
And so tell us about the future. Where does it go from here?
Yeah, so many of these customers are doing their big, huge training sets on top of AWS, happy to announce that many of them are also doing, as you mentioned, through that pipeline that you had up here earlier, they do their training, but they also then spread out inference.
Yeah.
And many of the customers tell us that actually 80 to 90% of the cost of machine learning at scale ends up being inference.
Yeah, this is the big market.
So super excited to announce this today. A new instance coming out in AWS, coming soon, the G4 instance. It'll be featuring NVIDIA T4 processors and really designed for machine learning inference. It's really designed to help our customers really shrink the time that it takes to do inference at the edge, where that response time really matters, but also really reduce the cost. They have to run fewer nodes. In addition to machine learning, where this is a really great fit, you mentioned you can also do graphics processing on these, and so we're really excited, and many customers are excited to do that as well. We have customers that are looking to do high-end video workstations in the cloud. We have customers that are looking to do video transcoding and media processing, as well as video game streaming, all of that via the cloud on our new G4 instances.
I've got two great stacks for you. One's called GeForce Now, the other one's called Omniverse.
Awesome.
Yeah, so you go build a whole bunch of cloud GPUs. I'll be there.
We will.
Nothing got me more excited when he said 61 countries.
That's right. 61 availability zones in 20 regions, but we're getting to 61 countries. That'll be coming soon. So we're super excited. I want to thank you. Hope you have a good show, and thank you for inviting us out.
Thank you, Matt. Thanks for the partnership.
Yeah.
Appreciate it. Thank you. Matt Garman, Amazon AWS, the largest computer on the planet. All right, Chapter 3, robotics. Here we're going to talk about robotics. The first part of robotics is Jetson. We created this little tiny computer called Jetson, and we put it out. It's based on Linux. It runs the entire NVIDIA CUDA-X stack. The amazing thing is there are 200,000 developers across 2,000 companies building things everywhere. Warehouse logistics robots, little delivery robots, agriculture robots, John Deere, for example, retail robots and assistants, industrial robots. Robots everywhere, augmenting our capability, doing things that are hard for us to do. And this area is just rich with research. This is, of course, the ultimate AI. Today, we're announcing a brand new robotics computer. A brand new robotics computer. We're so proud of this one. It is the smallest computer our company has ever built. It's called the Jetson Nano. I have one here. I've been wearing it all day. What, you don't get it? It took me days to get it. They kept putting the slide in front of me, and I kept, come on, it's not quite right. It's not quite right. His head's too big. Turns out it was my head. That's a terrible joke, you guys. Ladies and gentlemen, Jetson Nano. Here's the amazing thing about this little tiny thing. It's $99. The whole computer. And it's like, you know, if you use a Raspberry Pi and you just don't have enough computer performance, then you get yourself one of these. And it runs the entire CUDA X stack. It runs computer vision. It runs speech recognition. Because it's architecturally compatible. Our company is that way. And so you've got rich software and all the AIs that you've created that runs on DGXs. You know, when you compile it again, it runs on this. We care so much about the robotics industry, we decided to create a whole set of tools for the robotics, to foster the robotics ecosystem. And so today we're opening several things. The first is the Isaac Robot Engine, basically the entire stack that's available on top of it to create robots. It creates 3 different robots, the Kaya robot, the Carter robot, and the Link robot. And one of them could use little Jetson Nano, the other one may use Xavier. We also created a robotics simulator so that the robots could learn how to be robots inside this virtual reality environment, and it's gonna look like real to the robot, so that when the robot is done, and we take the artificial intelligent brain, we put it into the real physical robot, it sees the world, it perceives the world in the same way. The robotics loop basically has 3 things. And Guan talked about it, okay? Everybody talked about it. It's exactly the same way, however you think about it. 1, perception. 2, reasoning. And 3, planning. Perception, reasoning, and planning. Perception, reasoning, and planning. These robots are all doing that. The internet services, the AI chat conversational agents are doing that. The machine learning prediction systems are basically doing that. You're perceiving from all the data, you're reasoning about what to do, and you take action. You take action, you make a recommendation, or otherwise known in the world of physical worlds called planning. And so we would let the robot learn how to perceive the world, so the world has to look right. It has to reason about what to do based on what it's asked to do, and then it has to do the planning of the motion, the articulation of it, and do the work. We also wanted to learn the machine learning algorithm, the AI algorithm by itself, because some of these programs are just impossible to write. How do you look at something, go and pick it up, and the object is changing in shape sometimes. It's different shapes all the time. It's in a different position all the time. So the program's not exactly the same every single time, but you would like to have an agent, an AI algorithm that goes and picks it up by itself. And so we created a gym where it could learn through reinforcement learning how to be a robot. We put all these things together, and hopefully the ecosystem, the community can use this platform to create amazing robots for the future. You can go to developer.nvidia.com, Isaac SDK, and we'll just, you know, it's open, and feel free to use it, give us feedback. And let me show you. I saw it come, here we go. And there's these reference robots, they're just kind of, you know, here, come, just, you know, just stay put. Sit. All right, so this is Kaya, and this has a Jetson in it, and it's got rich sensors. In this case, depth camera. In the larger computers, the larger robots has LiDAR, and so they have wonderful sensors, and we can support very high-resolution sensors. And so if you wanted to make a little toy, you could. But if you wanted to make something that's actually real and you do real work, you can. And they can be wonderful robots. And the whole stack, from vision to speech, and all of the AI that we've been talking about, this whole time is available on here, and it should run, okay? And so, hey, good job, you guys. Kaya. Okay. The guys made you a short movie. Let's take a look at it. Ladies and gentlemen, Isaac Robotics, okay? Good job, you guys. Let me talk to you about one of the most important robots of all, your self-driving car. Everything that moves in the future will have robotics technology inside, will have some level of autonomous capability. Our company is deep in the middle of the autonomous vehicle revolution. But we're not building a self-driving car. We're creating a system and the infrastructure and the design capability necessary for the whole industry to build a self-driving car. These are basically the components of our Drive initiative. We start with, of course, the Saturn, what we call DGX Saturn V, our own supercomputer necessary for doing deep learning and training these AIs. The output of these AIs, whole bunch of them, that are then ensembled together to compose the three layers, the three groups of algorithms: perception, localization, and path planning. Perception, localization, and path planning. Some people combine localization and mapping, and so perception, localization, mapping, and planning. These three parts of the computing, AI computing stack, robotic stack, is inside the Drive platform. All of those algorithms are ensembled together to essentially create what we call Drive AV. Constellation is our simulation platform. As an engineer, nothing is right unless you can simulate it. You want to be able to simulate the corner conditions. You want to simulate the rare conditions. You want to be able to regress and repeat old scenarios. This car, not only does it drive by itself, but it has to communicate with you. Just as when Guhan was communicating with the cloud, there has to be visual back input, there has feedback, as well as audio feedback. And so Drive IX is our intelligent user experience, and it basically shows you what is in the mind of the self-driving car, and it communicates with you. The driving computer itself, scalable from level 2 all the way to robot taxis. We have a re-simulation effort that is going. I'm going to show you a video of that, and then ultimately, we've got to drive the car. We're going to drive the car until it drives by itself, and it's perfectly ready for production. And then we open up the entire platform. People could use it at the computer level, at the middleware software level, or the fully integrated application level. They could take advantage of our server system for developing the AI, the simulation system, and whatever infrastructure we've created. This is an open system. The future of autonomous vehicles has to be software defined. And the reason for that is because look at how far we have to go and how many different diversity of systems we have to support. It is impossible to design a specific widget for one particular car. We have to be software defined. It has to be open. You have to take advantage of the entire ecosystem. And I really appreciate all of the partners for joining us. Thank you. Today we're announcing our Release 9. Release 9. We're still a year or so away from having a production car, but this is our Release 9. High functioning level 2. It gives you off-ramp, on-ramp, and off-ramp. Last year we showed you I showed you how we drove 50 miles without touching the steering wheel. We have surround perception so that we could have the ability to do auto lane change. We localize to all of the world's major maps. We do real-time mapping ourselves. And the reason for that is because these maps cover about 80% of the world, but most of the routes that we drive ourselves, the last 20% of the world, it turns out to be the most frequent miles. And so our car could map, fuse it all together, and turn it into our own personal HD map that we can localize to in the future. We also integrate everything into an AR and VR system that I'll show you in just a second. It's really quite incredible. And then we have integrated driver monitoring and voice recognition. Basically, your car becomes an AI. Guys, let's show it to them. Last year, I showed you guys end-to-end 50 miles. This year, I'm showing you, this is map routing. Our car is doing dynamic mapping right now. You drive the routes, and then it fuses the routes together into a map. It doesn't record your driving, it's recreating the map. And now, notice on the right-hand side, it's creating a map. It fuses it together. Because of the routes that we drive these days, there's a lot of intersections, a lot of complicated intersections. We have to teach it what are the different contexts and where should you stop. Every intersection is a little bit different. Counting on red lights alone is not good enough. Counting on signs alone is not good enough. We fuse everything together. We have this great technology. This is so great. We use radar to localize. Essentially, radar turns into a LiDAR, very coarse LiDAR, and it works even in the rain and fog at night, and it supplements our camera. We simulate everything. This is a virtual reality simulator now. Automatic lane changing in a crowded environment. And this one is a technology called safety force field. Apply to brake. And then takes us home back to headquarters. Lots of intersections, lots of complicated corners. We drive it several times. We fuse it together into reconstruct our own map because the HD map of the map providers don't go here. Okay? In the interest, thank you guys. Let me show you something that's really cool. So the first part that you guys know we do incredibly well is perception. The second part we do incredibly well is localization. We've been building up the stack from the foundation up. Now we're going to introduce our path planning. Our path planning has several components. The first component is an ensemble of neural networks and different computer vision approaches to estimate the path that the car should take. We call that path planning. It is really robust, and it's fantastic. On top of that, we have a prediction algorithm to predict all of our surroundings. Detect the surrounding, predict its path, future path, estimate their speed. That action, perceiving the surroundings and predicting their future, is important to safe driving. And the reason for that is this. You want to be able to have a computationally robust algorithm to predict that whatever you decide to do, you will do no harm in the future. And so everybody else around you, assuming that they're well-behaving agents, that you yourself will computationally not cause any harm. So you are essentially in a safety cocoon. We have a method, a computational method, that detects the surrounding cars, predict their future path, of course knowing our own path, and computationally avoid the surrounding traffic. We call it the safety force field. This is the first of its kind. It's completely computational. It has the ability to be computationally validated. We have researchers around the world who are safety experts looking at the algorithms. We're getting great feedback from it. It's going to be an open system, so you guys can take the algorithm and you can implement it yourself. And let me show you how it works. So this is basically, you've now predicted that based on their trajectory, which is not moving, that you should apply your brakes. And this is, using this algorithm, you achieved what is called automatic emergency braking automatically. This is intersection handling. We're now predicting that car is now taking a turn, and so we have to apply our brakes, and we did it just in time. Okay, and this is intelligent steering. We're now estimating where everybody else is, and because we're blocked, we have to find the next closest route. Okay, and so that's part of the safety force field. It figures out computationally that there's a lane next to us, and we can use it. And this congested traffic, using computational methods, we detect where all of the surrounding cars are. We want to change lanes. It is okay to do so. And the reason for that is because we predicted the car velocity and trajectory of the car next to us, behind us, and we come to the conclusion that if we change lanes, it will not hit us. If we were to change our computation and we determine that it will collide with us, of course, we'll veer back into our own lane. Okay, so safety force field. Safety force field is computationally verified, and it is simulated, and that's why simulation is so vital to us. This algorithm, we're super proud of it. It's now going to be in the open, and you can read the white papers, and as we continue to progress, we'll make it available to you. And so the third stage of really, really great self-driving cars is the path planning algorithms, and both in comfort, in of course accuracy, in comfort, as well as in safety. Simulation is really vital. Today we're announcing that Constellation is available. We've been working on Constellation for some time. The architecture of the image generator is complicated. It's bit accurate, meaning the hardware, it's basically a virtual car. And you take the software, we throw it into our data center, and you essentially have a virtual car. It's like having a virtual fleet of autonomous vehicles in your data center. The workflow is in the cloud. You could program your workflow. We're going to show it to you in just a second. And then you could, of course, stream it from the cloud. In the future, instead of having thousands of AV test cars, we're going to have thousands of these Constellation systems. They're going to be so much more programmable. We can create conditions that we otherwise can't. And we have our own system all racked up. Okay, so now Mark is going to show it to you. Mark?
Okay. Let me show you a little bit about how we deploy our system on Constellation. You're looking at Drive Sim, which is our simulation platform. The center four screens are our simulator, right, left, front, and rear view. Thank you, Vanna. Over to the left side is the perception. This is the Drive AV stack taking the sensor input from the simulator and perceiving what's going on in the world, and as well as the lanes and the cars and everything that are in the world, and giving us control information back to the simulator, and so the computers are driving the car. Look, ma, no hands. Over here on the right side is what we show the driver, or the human in the car, so that the human is well aware that we're aware of what's happening in the environment. It's a confidence view.
As a driver, you could decide to see this augmented reality view right here, or you could decide to see a virtual reality view right there. And the ability to see this gives you so much confidence that the AV computer is recognizing, perceiving the right things, and about to do the right things. Okay, Mark, go.
Fantastic. So I want to show you how we actually use this, the workflow of using Drive Sim. So if we can switch to the developer view real quick. Over here on the right side, we're seeing yet another camera in the scene. This is a spectator camera that a developer would use. We're running the simulation the entire time that we're editing this. We also have a Jupyter Notebook Python interface to our Drive Sim, so we can make some changes. Let's make some weather changes. Go ahead. Let's nighttime. Go through a few of them. Sunset, rain.
So much easier to do this in virtual reality than to do it in real life. Like we try to hope for rain, but it just doesn't rain for months.
Okay, fantastic. So we've changed some environments in the world. We've actually been adding traffic as we've been playing along. All this while the simulation is running, all while we're running hardware in the loop. So we're talking to the actual computer in the car as though it's in the car.
The exact software that we would actually put into the car is actually running on Constellation. Bit accurate, exactly the same.
Perfect. Yes. So let's make one more modification while we're here. All this traffic is essentially, they're agents. They're running a paths based upon rules, but we can occupy the mind of one of these agents. Let's take it over and control it. So we've grabbed one of the cars in the world. Let's have it do a lane change. So I can locally modify any one of these bots of traffic. I can possess it and control it. I can set up any scenario I want interactively. Finally, the best way to test our car isn't to do all of this interactively. I really want some randomized versions of these scenarios that we just created, and I want to deploy them on a whole fleet of not real cars, but in this case, Constellation boxes in our data center. So let's do that. Let's switch to the Constellation view. Here we go. We've got, in this case, 12 versions of that exact same setup, but now with randomized variables of weather, time of day, timing of the traffic, so that we can test every possible perturbation of that scenario.
That's awesome. Thanks a lot, Mark. Thank you very much. Ladies and gentlemen, Constellation. Not only can you use it for simulation, you could use it for re-simulation. Watch this. This is really cool. What's actually happening here is we're taking a previous drive and we're taking the data and we're pumping it into Constellation. We're sitting inside a test car, stationary, outside. It's at GTC. As far as the car is concerned, it's basically running a regression. And so the detection is working, the lane detections are working, and its recommended paths are all working. And whenever there's any deviations from previous drives, this is how you can regress, do regression testing. Okay, good job, guys. Thank you. Constellation. I have one more thing to tell you. So it turns out that autonomous vehicles is one of the greatest challenges. Safety is a great concern. The technology is really complicated. The software that we have to develop is still quite significant. And it's a computing challenge. It's an artificial intelligence challenge. It is a system integration challenge of cars. There's all kinds of challenges involved. This is really one of the world's great computational challenges. And the world's largest car company is making enormous endeavors in this area. Ladies and gentlemen, today we're announcing that Toyota, the world's largest car company, the largest transportation company, is partnering with us from end to end. From deep learning systems, to simulation systems, to in-car computers, to collaboration with AI. Ladies and gentlemen, Toyota and the TRI Advanced Developments team is partnering with NVIDIA to create the future of autonomous vehicles. This is so exciting, and this is how we can make a real difference in the future of transportation. Let me quickly now summarize. We did several things today. We talked about accelerated computing and the path forward. Ladies and gentlemen, what does PRADA stand for? That's right, programmable acceleration of multiple domains with one architecture. Okay? So programmable acceleration domain architecture. That is what accelerated computing is about, and that's how we move forward. We work across the entire acceleration stack. The second thing is the future of graphics, the future of games is unquestionably ray tracing. You're going to hear about ray tracing on and on and on and on and on. This week turns out to be Game Developers Conference, and all they're going to be talking about is ray tracing. We announced several things. A server, graphics in the data center, a very complicated server architecture with 3 stacks on it for rendering, Omniverse, computer design, and 3, cloud gaming. On cloud gaming, we have a platform we call the GeForce Now Alliance, and we're partnered with SoftBank. LG U Plus is our first partners. And I'm so excited that we're announcing Omniverse, something we've been working on for quite a long time. It's just really great technology. The next, in data science, it's the new HPC. It's the fourth pillar of the scientific method. This is our ecosystem approach. And today we're also announcing two new computers designed for the future of data sciences and for enterprises all over the world to be able to access this technology. Data science workstations and a data science server based on the T4, and our partnership with AWS to take this entire stack on top of the world's largest computers to the world's data scientists. And of course, our partnership and our acquisition of Mellanox, something we're super excited about because the future of computing extends out of the computing node and into the networking fabric. And then lastly, in robotics, Jetson, the smallest little tiny computer, the cutest little thing right there. I'll just do it one more time for you guys, for your enjoyment. I think it's like right there. And and then Constellation, and then our partnership with Toyota. Ladies and gentlemen, this is our GTC. I want to thank all of you for coming today. Have a great GTC.